Hi everyone. So today we are going to look at snake and ladder problem, and it's a fun game. Almost every one of us has played it. But what if someone tells you to code it? Well, it is still interesting if you try to solve this problem as if you are playing this game and not just programmatically. So, for example, you have been given this board and you need to reach the destination cell from the source cell in a minimum number of steps. That means you need to roll the dice minimum number of times. So in this case, for example, if you are just starting, then you will first roll the dice 3 and then you will reach the number 22. Then you will roll 6 and you will reach 28. And then you will roll 2 to reach 30. So there are 3 times you have rolled the dice. There can be many other solutions like after reaching 22, you roll number 4 and reach 26 and you again roll 4 to reach 30. So there can be many solutions, but the ask here is what is the number of times you need to roll the dice to reach the destination, and that is also minimum number of times. So in this case the answer is 3. So let's try to think this problem in a different way. What if I simplify this particular board in a matrix manner where for every cell, if there is no snake or ladder, then I'll denote it as -1, and if there is a ladder, then I'll denote the destination cell of it. If there is a snake, for example in this case from 21 there is a snake to number 9, then I'll add 9 here in this particular matrix. So this particular matrix is nothing but the simplified version of this particular board. So can we imagine this particular matrix in a directed graph manner? So what do I mean by that? So for every cell, it's a vertex where there will be a destination vertex will be given. If it's -1, then you don't need to do anything. The number is that particular cell number itself. Otherwise, there will be a destination cell. And the distance will be nothing but the number of times you had to roll the dice to reach that number. So for example, you rolled 2 and you came here. That means the vertex here is 2 and the distance here is 1 because you just rolled the dice and you came here. After that, if you roll the dice one more time and you reach 2 and you reach 4, that means the distance will become 2 because you have rolled the dice once more. Alright, so this particular problem is nothing but the breadth first search problem because you are rolling the dice, everything is in your hand, so you are evaluating all the 6 neighbors of that particular number and then you are adding it into the queue, you are again evaluating all those neighbors and you are proceeding till you reach the destination cell. So as I said, this is a breadth first search problem. So what do we do in this breadth first search problem? So we create a queue, we add this particular cell, we evaluate all the 6 neighbors of that particular cell, we again add it into the queue and we proceed till we reach the end. So we also need to avoid repetitions. So if a snake takes us back to 9 and if we roll for example 1 and reach 10 and we have already evaluated number 10, then we can avoid that particular part. So we will also create an array of visited that will store the number 0 or 1. But first let's start with the queue. So first we will create queue. And this, as you can see, this queue will have every entry in this particular manner. And to start with, we will create a queue entry. Because we have not yet started the game, even the vertex will be 0 and the distance will be 0. So now we already have the queue, we have the starting point, and now as I said, to avoid repetitions, we will create an array. Let's name it visited. And it will have a size, that's the size of the board, the total number on the board, right? So now to start with, we'll first add the queue entry in the queue and then we will iterate over all the numbers, all the neighbors of that particular queue entry till we reach the destination cell. So while queue is not empty, we will pop the first number from the queue. So we have this number, and after that we'll know like what is the vertex of it. Why do we need this? So we are just starting right now, but imagine what if we are at the destination cell. We somehow need to know that we have reached a destination, we need to stop the operation now. So by taking V, that is the vertex of that particular cell, we'll get to know that. So we'll put an if condition here that if this vertex is the highest number, then just break out of this loop. We don't need to operate it further, we have reached the end. And if we have not, then we need to iterate over all the neighbors. That means in J, from V plus 1 till V plus 6, and we also need to make sure that we have not reached the end of the board. That means if I'm at 28, I don't need to go to all the 6 cells, because after 30, it's all done. So now we'll iterate through all the neighbors of that particular vertex. To avoid repetitions, first we will check that if visited of j is equal to 0, only then we'll proceed, because otherwise we already know that we have evaluated that option. So if we have not yet visited it, then we'll create a queue entry for it. And the distance will be whatever the entry that we have removed it from the queue plus 1. That means we have rolled the dice once more and then we have reached this destination. So now we have this distance. Now we need to reach at the vertex will be the destination cell of that particular vertex. So we first need to check this matrix. Like if the entry is -1, that means we need to stay on that particular number. So we'll check that if move of j is not equal to -1, that means it's not -1, there is some destination cell, then we'll put it a dot v is equals to move of j. Otherwise, we already know that a plus v will be nothing but j, means I need to stay on that particular cell number, right? And once we have all this information, we only need to add this in the queue and you are all done. It will again go to this option, it will again see all the 6 neighbors of that particular cell and it will reach the end. So let's assume that you have already reached 30. Because we have break out of this loop here, we have already reached the destination, and now you only need to return QE dot distance. That means the number of times you had to roll the dice to come on this particular number. Now let's see what is the time complexity of this particular algorithm. So what we have done is we have first added a cell into the queue and we have evaluated all the neighbors, but we only evaluated if we have not yet visited it. So for every particular cell, in the worst case, we'll only evaluate numbers once. So this particular algorithm will take order of n. Well, you are already also doing a for loop for all the 6 numbers. So in this particular case, it will be in worst case order of 6, but still it will become order of n into 6, which is nothing but order of n only. Thank you.